Hello, good morning, everyone. We are Group 3, presenting Dynamics Projectile Motion Homework 2, with our group consists of Christian Kenchem, Matthew Kanokong, Hubert Fernando Halim. The purpose of this presentation is to analyze the trajectory of a projectile motion, in which case we have selected a basketball as our object. The objectives are as the following: throw a ball like a basketball player, which they throw a penalty shot and record the penalty shot from sideways. Then from the experiment, we measure the initial velocity, both the magnitude and the direction. Then we match the experiment data with the analytical solution. With the initial velocity obtained with the experiment, we aim to answer, can the analytical solution explain the trajectory of the ball and the final position of the ball when it touches the wall? And finally, we perform 5 throws to get 5 sets of data, and we take the conclusions. Hence, we conducted the experiment 5 times, as shown in the following videos, where we recorded the player throwing the basketball from a sideways angle view. From these videos, we then measured the angles of a trajectory, the angle of launch, and as well as the displacement that happened from the basketball and from initial launch to a certain few initial frames after the launch point. The analysis calculations looked as the following, where we use a digital online measurement tool to conduct the dimensional analysis, which we then use the displacement equation for getting the displacement for the vertical and horizontal components of the direction of the ball. From the original equation, we can get the first equation for the vertical displacement, where we can see that the ball experiences an acceleration due to gravity. And so the equation is equal to the initial position of the ball added by the initial y vertical velocity multiplied by time added by half of the acceleration due to gravity multiplied by time squared. From this equation, we can rearrange to get the initial vertical velocity, which is the final position added by the initial position added by the half of the acceleration due to gravity multiplied by time squared, all divided by time. For the horizontal component, we can see that they experiences theoretically no acceleration, and therefore we can take out the acceleration component, which leaves us with the initial position of the ball added by the initial horizontal velocity multiplied by time, which results in the final displacement of the ball, which then we can rearrange for the initial horizontal velocity, which is the final position of the ball, added by the initial position over the time. We require both these initial velocities for vertical and horizontal in order to create the magnitude of the initial velocity, which is the square root of the sum of the the squares of both these components. Also, rearranging from the previous equations, we can also get the analytical trajectory, which we can then plot to get a curve that we use to analyze and predict the direction, movement, and final position of the ball after it has been thrown. We will then use this analytical trajectory equation to reference and cross-examine with the trajectory of the ball to see how well it matches up. Hence, from the 5 separate videos, we have measured and calculated the time using the previous equations. We've gathered the following initial velocities for 5 different videos, getting initial velocities ranging from 2.17 meter per second to 2.34 meter per second for the horizontal velocity, and velocities ranging from 2.416 up until 2.885 for the vertical initial velocities. The average turning out to be 2.237 for the horizontal velocity and 2.624 meters per second for the vertical velocity. By taking the magnitudes from 5 of these videos and getting the average magnitude of 3.44978 meters per second of the initial velocity. Hence, when we have plotted the curve using the following analytical trajectory equation into the calculator, and we have overlaid the results with the video in a sideways view. We can see the following results of the analytical trajectory and the actual trajectory. We can see that the ball follows a mostly similar curve and path with the vertical displacement. However, the ball does come fall short uh, of the predicted analytical horizontal displacement, where the horizontal analytical displacement is 0.287 meters. Meanwhile, the actual projected meanwhile the projected one is 0.22 meters. So why is there a shortage of the horizontal displacement? Where this is rooted in the fact that we have taken the initial assumption that there is no acceleration being experienced by the ball in the horizontal component, which in fact in real life there could be multiple factors that could affect these. For first, it will be air exerting a resistive force opposite to its velocity, which will be calculated in the following equation, where the air exerts resistive force that is opposes the horizontal velocity of the ball, and thus reduces the horizontal velocity during the flight, and thus decreases the amount of time, the distance that it will travel. Second, there will all be a ball spin or Magnus effect, where the rotation caused by the ball will create a lift or side force and redirects a forward momentum, and thus reduces the net horizontal range. Examined in multiple videos where there was a bit of a spin experienced by the ball while doing the throw, which was unavoidable. Furthermore, there's also the wind or the head cross, where the changes of the relative air velocity and increases the effective drag force experienced by the ball, which is caused by it being thrown in outdoors, exposing it to the wind. And finally, the fact that it was also a deflated ball. Due to the fact that the ball was deflated and not perfectly spherical, caused a turbulent flow, which further increases drag and causes additional horizontal deceleration. All these attributing to the fact that the horizontal displacement is not as uh, falls short of the predicted horizontal velocity, which could have been more accurate if we've accounted for these factors. And that'll be all for our presentation. Thank you very much for listening.